Okay, here we have up a sign 9e, problem number 4, a particle having charge Q equals 1.6, times 10 of 6 coulombs, and their mass m equals 0.01 kilograms connected to a string that is 1.6 meters long and tied to a pivot point P in the figure below. The particle, string, and pivot point all lie in a frictionless horizontal table. The particle is released from rest when the string makes an angle theta equals 60 degrees with uniform electric field of magnitude E equals 310 volts per meter. Determine the speed of the particle when the string is parallel to the electric field. Okay, so to solve this with energy, first we're going to start off our wall diagram. And so initially when the charge is at this point up here, it says velocity equals 0, so we know it's not moving, which means all the energy has to be stored potentially. But then once we're down here, we see this velocity arrow indicating the direction is down, but meaning that there is movement still, but it's also not at the bottom of its pivot, so there's still potential energy, if that makes sense. It can still go down to here before needing to wrap around again, meaning it would still have potential energy. Now, it doesn't mean that it exactly has half potential, half kinetic, but we know the energy is split between the two in a certain, to a certain ratio. Alright, so, okay, that's our length. The formula we're going to be using is let's say it's like to find our final, which is this, we're going to subtract the kinetic from our original potential. So our final is going to equal our initial potential. So let's do like minus the kinetic we find, and it is electricity, I guess, so we won't be using mgh per se, because that's more gravity related, even though charge is related to gravity. We're going to be using that our potential is going to equal to the charge times the electric field times the distance. So to substitute for that, I'll just do EF is equal to potential energy, and I just said it's going to be charge times length minus kinetic energy, and that's going to be 1/2 meters, not meters, mass times velocity squared. And then, well, hold up. This final is still potential. I gotta make that clear. So this right here is like this. I hope that makes sense. That should. It's like if I subtract this, I'm basically subtracting that from here. I mean, like all I have left is this. So I hope that makes sense. So once I start actually plugging stuff in, so this will still be like, it'll be the potential, so that I can cancel out the two potentials and then solve for the velocity. But yeah, so it does give us this L value that appears here, but that L value isn't what we're using. We need to find this, like how far down it's gonna go. That relates to the MGH principle, like the velocity. Like if I did it like this, mass doesn't cancel, yeah. But then the velocity would have to include the height at which you're falling times the gravitational field, but there's no gravitational field here, it's just the electric field. So I draw a triangle. Oops. This is 1.6, 90, 60, 30, and then we need to find here. So that would just simply be 1.6 sine 60 is equal to x, right? Opposite of hypotenuse, yeah. Yeah, and then okay, cool. Yeah, and just in terms of like make that make sense, I guess. So this, yeah, I guess I should reiterate. So this is still potential, this EF, and this is potential, but they're not from the same heights. So that was the whole reason I just did that triangle up there. So this potential, if I didn't like substitute numbers, it would just be QEL cosine of theta, and then the actual QEL. And this actual QEL is this. Minus 1/2 mv squared. And I can, like, I guess actually put this on the same side. So 1/2 mv squared is equal to QEL. Cosine theta. I'm gonna hold off a second and putting this 2 over there, and I'm gonna factor QEL. I have 1 minus cosine theta. And now I'll bring all that over. I can just do it in 1, I guess. And then, like, an easy way to get out the cosine theta is just this from there. 2 QEL, and it'll be 1 minus 1/2 because square root radians cosine 60 is 1/2. So yeah, and then I can do this. And I can go. I can just cancel this 2 into 1/2. So then it's just QEL over M, which is actually pretty interesting when you get down to it, that you can just skip all this and just go right to that. Like, the angle doesn't have an effect. Well, I guess the only effect it had would be the 1 minus. So yeah, okay, I guess it does still have an effect. It just has to cancel out here. I'm just gonna start back up here so I can see the picture again. Okay, we got that, and we're solving for velocity, so that's cool. Now our charge was 1.6 times 10. Oh, shoot, I did that twice. Yeah, that's that. Now let's see if it was 310 or 315. 310 volts per meter, I think. And then 1.6 meters all over our mass of 0.01 in kilograms. Center V is equal to 2817. And I'm gonna check this because I haven't done it in a minute. Yep. Meters per second. Oops. Meters per second. So yeah, I didn't even try this one the first time, all those weeks ago. Because I saw angles and I assumed torque somehow, being that it was a string from a torque unit, and that wasn't really my favorite unit, so obviously it wouldn't be the easiest for me, but looking back at it, I mean, it's all stuff I know, like this trick right here, this cosine theta. I was just looking for a way to not multiply by twice, and then Mr. Glenn's class came in my head, and I was like, oh shoot, I know what that means. So yeah, it's really not that bad once you just can't overthink it. I definitely overthink it. I saw 1.6 charge, or like coulombs, like I saw kilograms, I saw meters, and I was like, what kind of problem is this? I didn't even try it actually, but this probably took me like 5 minutes to remember how to do it. And it just, yeah, the wall diagram is a lifesaver. That equation is maybe a little different than the usual one, but that's just the way I thought of it. So yeah.